joining the seminar, for accepting the invitation to join this optimal seminar series. I'll start with a brief introduction to Anna, and then Anna will give her talk representation, and we'll try to have a few minutes at the end for discussion, for questions. Also, feel free to write on the chat. We'll try to keep an eye there. Or unmute yourself if Anna is fine with it, and pose the question directly to Anna.
Yes, yeah, we can make it interactive.
So,
yes, yeah.
Great, yes. Okay, so today with us we have Anna Radovanovic. Anna earned her PhD degree from Columbia University and then worked with IBM for a few years. And since 2008, she's with Google, now as a senior staff research scientist. And her research is focused on, among others, on electricity grid decarbonization. And she's also the technical lead for energy analytics and carbon-aware computing, which is very close, I think, to what she's going to talk about today, since the title of her talk is Carbon-Aware Computing at Google and Beyond. Right, Anna? So
Yes.
once again, thank you very much. The floor is yours.
Okay, thank you, Stephanos, and thanks for your patience in our communications in preparation for this talk.
No problem.
And so I just want to tell you that this talk I gave exactly the same one because it was more convenient, and this is the current state of the world. The present 2 days ago in FI Performance Conference 2021. So those who were there and who listened to this keynote speech of mine, this is exactly the same. But maybe you have questions now to ask me that you thought of like in between these two talks. And in the future, like I will leave 10 minutes for questions, but in case you have more, today I cannot stay longer, but we can organize another session with questions and just Q&A. So happy to organize it with you. Okay. So hello everyone. So as I said, I'm going to talk about carbon-aware computing at Google and beyond, what that means, what are the challenges and opportunities that we have faced in order to build a system for that, what drives the carbon-aware computing, and what are we working, the challenges that we are facing even right now. Also, I'm going to provide some insights of how we are planning to scale our systems and products inside and outside of Google, and to facilitate faster decarbonization. Also, I will share some of the opportunities that we see even now, not only within Google, but something that can happen wherever, even outside. So all that I'm going to present is a subject of really great collaboration with the experts all across Alphabet. I mean, this is not a 1 or 2 year work. This is like a result of close collaboration with experts across different domains. As you know, energy is such a domain. So what is carbon-aware computing? So this is exploiting flexibility in when and where and how computing is done to reduce carbon emissions. So before going into these, the natural questions, why we think about data center loads, what do they matter at all? And this is actually nothing of ours. This is an excerpt from the recent work science paper where it is shown. It's a very interesting paper, just really as an insightful paper, which says that the demand of computing resources in data center power, associated power, has grown worldwide, has been continuously growing, and now it's approximately around 1% of the total electricity usage. What is interesting also that only between 2010 and 18, we've seen that global data center workloads and computing instances have been growing continuously and grew to be sixfold, right? Just from this time horizon. What I didn't put here is even more interesting fact. Even though computing instances and workloads in amount grew sixfold, right? The associated power usage actually grew only 6%. And this is mainly because in parallel, there are many power efficiency efforts, right, in a data center world. And what is the biggest deficiency, right? Like gain, what happened when in moving the data center computing from traditional to hyperscale and cloud computing, which is much more efficient, designed specifically to just really reduce the overheads. And the main premise of all our research and study and development was that cloud and hyperscale computing data centers with some load flexibility can change the load patterns in the grid in a planned manner. And what then? Well, we believe that we can influence electricity markets and hence affect the carbon intensity and facilitate the grid carbonization. So this is where we are. This is what motivates our work. So talking about flexibility, which I believe is the most important topic here, because this enables all that we're talking about, is that there are workloads typically that have flexibility in when they can run. So typical examples are all those data compaction and distributed computation pipelines for processing videos, feature extraction, training large-scale machine learning models to optimize for web search, content, and social recommendation systems. Then simulation pipelines, oftentimes you can schedule to work at specific times of the day, right? And many other latency-tolerant workloads that we typically refer to as batch. And this is a dynamic figure that I took from our first blog post in 2020, where we tried to actually announce that we have now a big pilot running and which shifts compute workloads in time and aligns them better with the carbon-free generation in the grid, right? So, and since then we launched in April the same year, and we started our global launch, and now this system has been running for 2 years. Finally, then there is something else, and there are many important workloads that are user-facing, and they have flexibility in when they can run. And I love this example with user-facing services because I'm thinking about a lot about them. Which can be typically geographically rebalanced and resourced, right? And all these requests for cloud applications like Microsoft Office, Facebook and Twitter messaging, Salesforce Enterprise Solutions, Google's G Suite, YouTube Maps. Typically, these requests you can actually reroute and you can meet the demand for them at different locations. Obviously, the latency is a constraint that we need to think about, but this is the fact that this can be done. Also, compute resource sourcing, how large cloud providers can meet the demand from their cloud customers and assign them pods on different data center location is also something that can be made CarbonAware. And here we have like a list of like Amazon, AWS, Azure, G Cloud, IBM Cloud. We all are trying and thinking about sustainable solutions. And there are two systems that are recently announced, if I can say, or products. The one is the announcement from 2020. This is Microsoft's CarbonAware Kubernetes, right? And which is a dynamic allocation using marginal carbon intensity. So using the carbon intensity data, and I will talk about this data more later. And earlier this year, Google announced that Cloud's region picker, which basically provides cloud customers an option to choose the location based on the percent of carbon-free energy in the local grid. So it's very interesting. And we hope to see more of these solutions. So this is like a dynamic figure again, is from our more recent post this year when we announced that we are shifting flexible compute workloads, not only in time, but across locations. And this is what we started piloting in February this year. And to align to actually, we are moving the workloads away from places where it's really, where the local grids are really carbon intensive to the cleaner grids. So the idea in theory about all of this is not entirely new. The theoretical treatment, small-scale prototypes, simulation-based study existed, and we've been reading a lot to actually see what happened in the past and realize this is a 10-plus-year-old idea. And here I'm just listing some of the papers in that cover compute shifting across space, compute shifting in time, and data center grid integration. Right. However, what we realized is that this was all very nice, and people tried to affect and come up with the solutions, optimization frameworks, trying out how, like measuring a potential impact, but actually to build the real system, we needed new theory, data, and engineering. And we call it carbon intelligent computing system. And the flexibility that we are trying to utilizing in compute was enabled and became manageable thanks to availability of carbon intensity data. So understanding how the carbon intensity changes in time and across grids. And we partnered very early on. I was doing some research and I partnered with Tomorrow, it's electricitymap.org. And then through our collaboration of just studying the energy generation mix on the grid, we realized that we could do all of this research, really. Then also what enabled building a system and scalable infrastructure is the scalable infrastructure helps build sophisticated and scalable solutions. Then we very much rely on virtualization and migration mechanisms for VMs, which helps us actually do shifting across space. Then what helps is also understanding what is flexible load. We needed to understand and identify which load is flexible, shiftable in time, shiftable space, none of that, and so on. Most of the theory so far that we developed, though we expanded a lot of them in the last 3-4 months, is actually captured in this paper, which is currently under the review. Our paper, CarbonAware Computing for Data Centers. And I'm just, to the best of my knowledge, I'm just going to mention the 3 deployed large-scale solutions so far. It's Google's Carbon Intelligent Computing Platform announced in 2020, then Microsoft's CarbonAware Computing, which is developed to place pods and source resources for cloud customers. This is later in 2020. And earlier this year, in 2021, we announced that we are shifting, as I already mentioned, workloads across data centers within the same continent. So the vision is to use flexibility to reduce emissions. So there are actually 4 approaches in doing that. And while I'm mostly going to focus on the system that we built, there are 4 approaches for increasing carbon awareness, and we are actually trying to spread the impact and work on all of them. One is user-facing, okay? Do carbon reporting. And through carbon reporting of the footprint to customers, they are going to actually, and even internally to developers, we are growing their awareness of how much footprint they generate. Then there is a developer facing is through carbon signaling. We can be sharing either like carbon intensities or carbon efficiencies that we compute, which are also a function of power usage of their code and implementations, right? And that we can influence them in how they design code, how they schedule their pipelines, and so on. The infrastructure is what is really probably the most interesting, because we build the intelligence to identify flexibility, characterize the flexibility, and manage the flexibility, right? Optimally. And this is what I'm going to spend most of the time talking. And there is also re-engineering. It's not only with what you have in flexibility, but there is a huge trend currently to actually increase the flexibility in workloads and make them flexible so that we can actually increase the impact of the systems that we build. So there is briefly a screenshot of our application, cloud application, that is currently provided to only some of the cloud customers. And a colleague of mine, who I believe was from your lab, worked a lot on methodology, Ian Schneider, on methodology to actually capture the build, to capture the and approximate energy consumption of different cloud users, their monthly cloud carbon footprint reports, and to segment them based on their services, products into these monthly reports. This is announced a month or so ago, right? This is a very new thing. Next, their Google Cloud customers are offered this solution, which is really cool. So they are able now to choose where they want their resources to sit based on their latency tolerance of their applications, right? We have provided a % of carbon-free energy in the local grids, and they can choose, the sourcing locations. And it was really, really well-received product. And now let me just move. And if you don't have any questions, I think this is now the core of the talk. I'm going to describe the system that we built. So what did here the focus is building this carbon intelligent data center load management platform. So what we are trying to do, we have a portfolio of data centers that sit at different locations and different grids, right? And we tried to build the central mechanisms that is going to shape the workloads in such a way that to reduce carbon emissions. In order to effectively do this, we needed to harness not only the flexibility of our workloads, but we needed to actually harness the dynamics of electricity markets where our data centers sit. So we realized that very early on, and we still are actually trying to accomplish some of these goals. And I'm going to mention a type of research that we are also conducting right now. Early on, we asked ourselves, where are all the opportunities that we have? And what we understood very well, that power usage of our computing really depends strongly on the hardware that we implement in our power domains. And you can see that different data centers can have very different watt per CPU usage across locations. And this is highly dependent not on CPU use or workload type, but on hardware application. Next, we understood that peak power usage versus mean power usage across different clusters is also different, right? It can vary. It's approximately 5%. As you can see, this is the histogram across different clusters, which means that there is an opportunity to affect, if we shifted load, of reducing peak power usage in this cluster. And this way, we can actually reduce the capacity needed to meet the demand of our computing. And this is something that can actually reduce the amount of bills and make our fleet more sustainable. We don't need to order that many machines. We can meet the same demand and even larger demand if we have shifting. We can meet larger demand with less machines. Finally, this is a very strong signal, the one that you see on the right-hand side and in the bottom of the slide. This is the diversity in carbon intensity across different regions. Obviously, the portfolio of generation that meets and powers the grids where our data centers sit is quite different. And you see that these are 3 locations where we have data centers. One is in Finland, far the cleanest. One is the Midwest, and one is which in the middle of the day is powered mainly by coal, like a majority of the generation comes from coal. And there is a Singapore, which is really mainly coal and natural gas and oil, but mainly coal and oil. So you can see how there is some discrepancy that first also within a day, how this carbon intensity changes, but the major discrepancies is across locations, and this is why we are so much after shifting across space. So what have been the challenging and the key opportunity that we identified and that helped us actually, like, was the core in building the new system? So the challenges, and these are kind of a constraints, right, that we need to work with, is that whatever we do, however we build controls to manage our workloads, we needed to respect reliability principle. This means that if we change the control algorithms to manage and like affect loads in real time, we need to do that in such a way that if we push new signals and we see that something is wrong, because something we can easily break and like implement the augmentation and it can go wrong, we have to be ready to push it back, to revert it, to go back to the original state. And so everything has to become and happen gradually, right? Also, when we do planning and planning of this shifting that is going to happen, we need to take care of hard infrastructure constraints. These are machine capacities that we have, and only beyond that, we cannot expect more load to be processed. Then there are circuit breaker limits that if we don't respect these limits, there are mechanisms to actually respect them, but if we don't, we can actually turn down the whole data center and affect not only the flexible load usage, but affect the search and very core applications of Google. There are workload performance expectations, because as you can imagine, there are different types of workloads, and people purchase resources to meet the demand of different types of workloads, and they have their performance expectations, latency tolerances. And so we need to meet and comply with this to make sure that we have service level objectives that we are actually respecting at all times. What we learned also, and we are aware that when shifting jobs across space and in time, we need to understand what their dependencies, not only the dependencies to other jobs, but dependencies to also storage and data requirements, because this all comes together, right? And moves together in a way, or delays something. If we delay a job, we will delay maybe the overall process. We learned also that job resource requirements only for a single job, if you look at distribution of resource requirements throughout the lifetime of a job, they're quite diverse, they're quite volatile, and this distribution, like, there is a lot of uncertainty. So really working and trying to capture this uncertainty would be a tough job to do, and actually probably I don't know how manageable that would work. Many people try to do that, capture such an approach in the papers, but we found it very, I think, infeasible for our purposes. Another important thing is what it means to change the scheduler. It's a big problem for Google. Like, job schedulers complexity has to be super lightweight. Job scheduler makes hundreds of thousands of decisions per second, and trying to change the algorithm of a scheduler to delay a job, not to schedule a job, right, to place it somewhere else, it's actually so complex that we cannot really like add optimization layer there. This is very impossible. So, but what then worked for us with all these constraints, which seem to be very, very like harsh, and this is that very early in the project, we discovered that the total amount of work that needs to get done, like throughout the next day, so this flexible computing, is the total amount is quite predictable. So what does it mean? That if we have this total amount, we can actually mold it in the course of the day. We can treat it as a squishable fluid that can be moved and reallocated throughout the times of the day. You know, we can plan for it and compute some kind of envelope that will squish load and let it run and push it to some later times, right? And also we extend this, I will show you later, the application to shifting across space. And this is the core principle. So we work with this aggregate amount of flexible computing within the same day. And what we are trying to do is compute this optimal shape. So let me just move to this slide, which conceptually should, and the next two slides describe exactly what we do. So we build a new system, new component in the overall system. This component didn't exist, the component at the top. This is a purely analytics component, and which does day-ahead carbon and efficiency-aware planning. So the component I will show you later does forecasting and computing of the optimal envelope, which we called Loadshaping Guideline. It does it, right? Compute these guidelines for different clusters across the fleet. So each cluster gets its guideline. And you can see guidelines are these red curves here. So they are pushed daily. And what they do, they like, instead of having the organic, this black line shape, load shape, it tries to actually like squeeze the amount of resources provided to flexible demand away from time where the carbon intensity is high, and also away from locations where the carbon intensity is high. So we are basically having a guideline that just really does, squeezes out these flexible compute from times and locations where the intensity is high. This guideline is kind of like, not kind of, this is actually the constraint for a real-time scheduler. We didn't change the scheduler logic, but we are tricking the scheduler to believe that it has a different amount of compute availability depending on the carbon intensity of the local grid. So, and this is exactly what happens. So let me just show you these load shaping guidelines we now call virtual capacity curves, right? Just because they're not true capacities, but they were like in this graph, you can see this brown line would be the machine capacity of a cluster. But what we are trying, our analytics layer computes the capacity curve here, this in red line, which is different from machine capacity, but scheduler believes that this is the new capacity curve. And it uses it to schedule flexible computing. And what it does at the times of the day when this capacity is low, what happens, the scheduler will not schedule these flexible applications or jobs, tasks. So it is going to put them into they're going to sit in the pending queue and wait for the later time of the day when available resources that were available to actually schedule and assign resources to these jobs that are waiting based on some priority rules. They are priority and right first come the time of arrival and other things. But basically it turns out that this, as you can see here, so this orange block is going to be executed first. This blue block probably is going to be shifted even early next day morning. But these are the time here in this example, early morning and late in the evening are low carbon intensity times in this grid. At the same time, this purple line is the amount of, like this is the inflexible. So the gray line, let me put this, is the total workload usage, out of which this purple is actually inflexible usage, which we don't affect at all. So the system in this design in such a way that actually scheduler for inflexible workloads, those serving workloads, is completely independent from a scheduler of flexible workloads. So what is going to happen, like our flexible load scheduler is going to just check in the difference between this red line and purple line in coming up with how much available capacity there is. So, and never ever this red usage is going to exceed this red line. In this graph, you maybe noticed that that not only that we change the shape here of the load, but also that we reduce the peak power usage, compute and related power usage in this cluster. So this was an amazing opportunity for Google because we are addressing not only the carbon part of the story and sustainability part of the story, but also we are addressing at the same time efficiency problem. So after, when we realized that, because it would have been very hard for us to just work with carbon objectives, we like, and also it doesn't really make sense. If Google has to buy so much machines to actually to accomplish the carbon objective, then it is not worth it, because also buying machines is not really like a sustainable solutions as well. So with this project and these mechanisms, we also accomplished, right, reaching efficiency goals. So what makes this approach effective? So the key, as I mentioned, is the predictability, next day predictability of demand and grid level carbon intensities. So we have our pipelines that we are going to predict both the inflexible and daily flexible compute usage. We have pipelines that map compute usage and to power usage, because we need to understand what is the implication of shifting compute on power usage, right? Then we have also like pipelines that source using electricitymap.org's API. We source carbon intensities, expose them right to our pipeline, and this data is continuously refreshed and used, right, for both monitoring and this planning that we do for shifting. Also, what is made this solution scalable is that this shaping is just a constraint. We don't make scheduler more complex. It uses the computed curves only as guidelines, and it operates with predictable quantities, and this is the total aggregate demand. And this luckily is predictable, so that we could actually come up with a very simple optimization, like, I don't know whether it's simple, but it's very like compact optimization, exact optimization solutions and framework that exactly really gives us the curve, and this as a load shaping guideline. So it was really, we could run a global optimizer that does all this computation for us. And it's not a problem even if the number of clusters doubles in the next year. The optimizer is truly like we decouple the forecasting from optimization, and everything works really well. Also, the framework, optimization framework is scalable. We can enhance, add constraints, whether these constraints are some new spatial shifting constraints. We can add potentially like storage constraint, energy storage constraints if we have them. So we are thinking about it a lot, but even since our first launch to now, we managed to actually, now we are working with constraints that enable spatial shifting, right? And we are using this as a guideline. So whenever we see that the capacity drops significantly in a cluster, the spatially flexible workloads are going to look around and for locations where there is enough capacity to meet their demand. And typically the places where there is capacity are also green locations as well. It's very important. The risk awareness is super important for Google systems. So, and luckily the approach we came up with has explicit characterization of performance expectations, whether it's a workload performance expectation, for example, the amount of work that needs to be done has to be completed within 24 hours, or prediction uncertainty of resource and power demand needs to meet certain performance bound, or power infrastructure limits need to be met, or energy at no time, at no time, power usage of the whole data center cannot exceed some energy contract limit. So all of these we explicitly write into the constraints. And this is how the system looks like. This is really the components of carbon intelligent computing systems. We decouple them. They run daily, in highly parallelized manner. Power modeling for each power domain, and I will show you what the power domain is. Like for each cluster and each power domain, we train the model that maps the CPU, or here we call Google Compute Units, usage to power usage. Then there is demand, day-ahead demand forecasting. There are pipelines that actually extract data, pre-process data, clean data, and prepare, right, these capacity constraints, energy constraints, performance expectations, also collect all kinds of information that we put as parameters into the optimization. And this is a global optimization framework, because when we start shifting across space, the curves, these guidelines, how we call them, they're actually dependent on each other. So they are all outputs of this global optimization framework that tries to minimize carbon footprint and peak power. These lambdas are just parameters. That is kind of something like coming up with the internal carbon cost for us. And we push these curves, and these curves, when they are computing, they are pushed, and then they reach all the clusters across the fleet, and they affect the next day load shape of all these clusters. Obviously, this is not an open loop system, because we need to be super aware what we do to the workloads. We affect it every minute, every second of the day. So if something goes wrong, we actually have monitoring that detects potential performance violations, and we have mechanisms that we apply. For example, if we notice that we are persistently with high probability, like pushing not meeting the throughput or daily demand of flexible usage, in some of the clusters, we disable shaping in them, because we conclude that possibly our load forecasting needs to catch up with some new load trends or something. This happens very rarely, but we need to have a mechanisms to address that and detect scenarios when it really happens with high probability. So this is what we do. So here are some screenshots I wanted to show you, because we claim that everything is thanks to the predictability, and the effectiveness of our system is thanks to the predictability. Here I scanned, took a screenshot of from a dashboard which shows forecasts. On the top graph, you see forecasts of daily flexible compute usage of a cluster. So the blue line is the actual daily demand. A red line is the prediction. A yellow line is our risk-aware flexible capacity. So we never work with point estimates of next day demand. We work with risk-aware estimates that ensure that with probability larger than 97%, for example, something that we define within an SLO, we are going to meet next day daily demand. So this is what we do, and you look at how much we save in a way. This green line is available machine capacity for flexible workloads, and you can see that a drastic amount is in the end not used from what machine can provide. And you can imagine what could be potential applications of things like that, right? And in increasing the power efficiency, right? So median absolute percent error in predicting this flexible daily demand is smaller than 20% for more than 90% of clusters, and it's smaller than 10% for approximately 60 clusters, right? And if I showed you the intraday pattern of these loads, they're super volatile. So it's impressive that you achieve this accuracy when you aggregate. I mean, maybe it's expected, but it's good to see that we achieve this prediction accuracy when we aggregate and look at the daily demand, right? Found a way to deal with aggregate demand. On the other hand, there is the intraday inflexible demand. These are load serving. This is what we don't touch. We are not now affecting at all. This is, for example, part of this demand is what serves your search requests, right? So you see that blue line here is also the actual load pattern, and the red line is what we predict. And median absolute percent error is smaller than 8%. This is quite predictable demand for more than 90% of Google clusters globally. Next are the power models. This is like when we shift, how do we know how we affect power usage, right? When we shift compute, and this is exactly what we, there is a vast amount of research that try to answer this question, and this is not surprising actually. There was some previous work that we used, and then we a little bit enhanced the way we do it, but we showed through like extensive experimentation that a piecewise linear model is an excellent model to map CPU usage of a power domain to power usage. And why power domain? These are kind of sets of racks that sit in a data center. Several power domains comprise a cluster, and each power domain is metered. So which is super important because we could validate that these models work, and we train them daily, and we actually have extensive daily validation of these models and measuring of error. So mean absolute percent error is smaller than 5% for more than 95% of all Google's power domains, which is also the many thousands of these domains, and this is excellent, really, performance. Finally, but very importantly, how we do our thing depends hugely on our vision and visibility to how grid performs and what happens on the grid. And we currently use the average carbon intensity forecasts to understand what's planned and what the grid is going to look like next day. So we use Electricity Maps API, and their forecast have been great. They provided forecasts for all the regions globally where we have our data centers, which was really important, obviously. A little bit on the optimization or the co-optimization. Obviously, you already probably noticed that we do these trade-offs, right? Why it's a trade-off? Because sometimes if we didn't have this efficiency term, we could squish all the load to the time and try to push it to the time of the day when the carbon intensity of the local grid is smallest. But then we would extremely increase power usage peaks, and we would need much more machines to actually meet this demand. So there needs to be some trade-off between efficiency and carbon. In some cases, which are not actually rare, but there are a few locations where typically they're aligned. What I mean is typically in the middle of the day when the carbon intensity of the grid is high, for example, Midwest, we also see that organic load shape peaks at that time. And by pushing, reshaping to push the load demand usage down, we accomplish both. We increase the efficiency, and we reduce the carbon footprint of these clusters. So this optimization, so everything day ahead is computing and performed daily, and the curves are pushed and they're shaping the load the next day. So let me show you some demonstrations from the real impact from our load shaping. So what I wanted to show with demonstration is how the flexible load amount affects the impact, how prediction uncertainty affects the impact, and how variability and magnitude of carbon intensity forecasts affect this. So you can see these are real life examples from 3 clusters. In the first 2, on the top 2 rows, you see the cases of clusters which have a very large amount of flexible compute, right? What is different is that in this first case, you have large variability in the demand. So we needed to provide a lot of capacity here to make sure that it's going to be met. However, we still managed to have a very drastic drop in capacity at the times of the day when this black line, which is the carbon intensity curve, is peaking, right? So you can see the effect on load. First, load is the blue line, but here you can also see the effect on power load, power usage, right? So you can see how power usage drops when we drop the capacity and therefore this compute usage. So we managed in this case of these clusters to drop power usage by 8% for 3 hours at the peak carbon intensity. Right, 3 hours in the middle of the day when the carbon intensity is high. There is a second row which shows also has a huge amount of flexible compute, but what you can notice here that we could actually drop capacity for a longer time and therefore make a impact is long enduring, right? It's lasts for 6 hours here because we didn't have to provide that large of a buffer between the provision capacity and the actual load, because this risk awareness of our methodology is an important property we have SLOs to meet. The third example was deliberately chosen to show that we don't achieve the same impact in all clusters because we have clusters with a very little amount of flexible compute. And typically when it's very little, that you can see also that it's very fluctuating within a day, and very often even aggregate amount, daily amount can be very uncertain. This doesn't happen often, but we have these scenarios where we don't really we cannot say with high certainty that we affect and achieve carbon-aware shaping really at all. This is a little bit of a different perspective, and this is a perspective where we look at normalized power curves of different clusters, and then we average them out across clusters within the same campus. Because what in the end matters is how the data center overall is seen by the grid, right? So this blue line would be the organic, a normalized load shape, and or the baseline, and the orange line is the effect, what we get when we shape. The green line is the carbon intensity curve. So you can see 1 to 2, and in some moments 3% reduction, and someone can say, oh, this is so little. This is not little, given that actually data centers are hundreds of megawatts in power, even though we are believing that we can achieve more, and we are working on increasing and understanding how to increase the flexibility and more effectively manage it. But this is what you can see as an outcome of carbon-aware load shaping. This is the effect on the aggregate normalized power usage. What are the open challenges? And I alluded to some of them, and I'm going to finish soon. I see that we have 10 minutes. So first, understanding flexibility. We've played a lot with different parameters, and we understand that actually, even though that characterizations of actually flexibility is very important thing. What is latency tolerant? How should we describe it? How we should capture it within the optimization frameworks? This is also important. For example, when we started shaping more aggressively to increase the carbon impact, we noticed that some users started complaining. What are you doing? You know, you're preempting my job so frequently, you are messing up with the performance. Our other pipelines that depend on these jobs are affected. So we are working for these hurdles, luckily, to come up with the best solutions while our system is working. So, and this is our biggest challenge right now, because not only that we need to understand the flexibility, but we need to also grow it, find mechanisms to grow. So I mentioned already this effect of load shaping, that we try to understand why this happens and what we could do even engineering wise to reduce it and to make applications more susceptible to this. Also, what you probably picked up is that this mechanism that we propose is excellent in pushing the load away from times and places where the carbon intensity is high. But what we have figured out, what we want to achieve is also find some attractors, identify signals that would also guide these workloads and jobs to actually to go and request demand, go and ask for resources at locations where which are particularly like green or low carbon intensive. So this is what we are working on. Finally, like a core question for us, which we are obsessing for some time, and now we're trying to find a way to work on that as well, is how are we affecting carbon dioxide emissions with all this shaping? Why? Because so far, yes, our objective is carbon footprint, but electricity-based carbon footprint is not really also completely, it's directionally the right thing, but we don't know to do, right? And it takes us, probably gets us closer to where we want, but we want to understand how we affect the emissions of the dispatch generation. And this is what we are starting to work on more intensively. And now I'm going to finish because I'm leaving only 7 minutes. I apologize for that. But what we want to say is that the opportunity is now. There are many, many areas where like industries, different participants, academics, researchers, right, can make an impact in many different ways. And it's just kind of exploring different opportunities. And this is what we are trying to share this message and enable others to do similar things, right? Either through CarbonAware cloud control devices, right? Internet of Things, or through what we do, expose data, or through finding a way to effectively migrate applications to grid cloud regions, and empower cloud customers to do similar things with their own workloads. So thank you all.
Thank you very much, Anna, for the great presentation. Thanks a lot. We have, I think, about 5-6 minutes for questions in order to respect the overall timing of the seminar. I think there are already a few questions in the chat. I can try to read them quickly to you. The first question is actually from Maria Illich. She's also from MIT. And the question is, whether Google can today
Stefanos, let me make it shorter because I think we don't have time.
Yeah, thanks,
the question is very elaborate, but all what I'm trying to ask is to say that by listening to you, I think you're just doing adaptive load management rather than direct load control. And you are pointing out that the end users can do this. And my added comment is that ISOs will never be able to shape your usage in top-down direct control that way. So the hidden question is there, what needs to be changed in markets so that you move a little bit from this direct load control to more adaptive load control? A very short summary of, the second question is, I know that, is it possible, this is a clarification question, can Google buy from an ISO in the area where they are not located?
Buy from directly purchase energy,
right. And that right away gives disincentive to what you're doing. Yeah. So that is the big question. Yeah.
Okay, Maria. First, yes, we are doing adaptive load management, but whether you can, I think we see the Google response through our signaling. So there are parallel efforts. With what we have, we can learn the flexible demand and we can try to shape it, right? In the market, there are ways, as we know. This is exactly the right questions. And through our study that I mentioned, just carbon emissions impact, we cannot do this study alone. Mm-hmm. We are going to partner with a particular ISO, hopefully, and study what really happens as a result of this load shaping, especially when it starts happening at scale. How are we going to affect the dispatch? And this is, like now as a sole local with this localized or global control, but this is just one node in the grid, particularly in the ISO. We are doing minor changes, but effectively we are hoping to influence the others and understand what kind of distributed control, how the market and loads in the grid should, like doing CarbonAware load shaping, how they should actually cooperate to maximize the impact. I hope. So we don't know how it's going to, this requires a new design, but first it requires our understanding how these load shaped affect the dispatch. And this is what we are planning to study. So I don't have an answer to you. This is exactly what we want to do.
My point was exactly that what you're saying makes perfect sense. It's just that we have to work on the market rules too.
Yes, exactly. Yeah. I totally agree. And there needs to be some cooperation, right, between the ISOs and to your question, currently we have this binding agreement. Somewhere in Europe, we tend to buy bulks of power, but we want to change that, right, to kind of be more adaptive and time dependent, right, not just to purchase blocks, right, or so we will see how we can incorporate mechanisms that we build internally with what we can do, like in terms of purchasing agreements. Right.
Thank you.
I think, yeah, there is also a question from Alberto. Please, Alberto.
Hi, Alberto.
Thank you so much, Stefan. So I'm just going to be jumping the queue, and I apologize to the others because it's actually related to this. The clarification question is, right now, do you buy your power through contracts? Or what kind of visibility does the ISO have to, like, regarding whatever you're buying? Is this, like, are you bidding directly into the market? Or is it, okay.
No. We've been trying, we would like to go there because there is nothing, unfortunately, regulations are stopping us in US, right, are stopping us from that. And our strategies are working hard to actually, to change that. So we are now, this is why we had to apply something like that. I was obsessed by that question, why not? Why not? And this is why this is like a passive way of responding to what happens in the market and using carbon intensity. You can at least that no one prevents us from shaping just by looking at these signals next day, which are quite predictable. So yeah, yeah, you're welcome.
Well, I know that there are mentions, but the time is a bit.
Maybe one question more. I feel bad.
Yeah, okay, let's have one more.
I just had a follow-up on what I think we were just discussing right now. So I just heard recently that Google is one of the biggest power purchase. I mean, they're buying these power purchase agreements, which give you guarantee of origin. So just like adding a bit that, I mean, I think Google is already one of those who is like trying to buy a lot from renewable energy sources. So I think it was kind of in sync of what is being discussed.
Yes, but you know what we're trying to do, and this is a 24/7 idea. So the question is an interesting concept that gets us closer to decarbonization world, but it's not really, because we know that we have all this grid network, right? So we invest a lot in power purchase agreements to inject a lot of renewables in the grid, but our data centers are not co-located. So it's still like we're trying to cover up for the annual demand, and now 24 time-wise, you know, intraday demand of what green energy that PPAs that we sign the contracts for generate within a day. But it's still, right? It's something that it's not totally like it's not totally right, how would I say, zero carbon solution, right?
Thank you.
Thank you very much. I think let's try to wrap up here because I know that Anna has a pretty busy schedule. Anna, I would like to thank you again for accepting our invitation and for joining our seminar series. And thank you everyone for participating.
Yes.
Yeah.
And I would like to add, if there is an interest in discussion, I couldn't move the commitment this morning, but if there is an interest in discussion, having a discussion after this talk, related to this talk, I would be happy to schedule something with you. So
Great.
Just please let me know if there is, if you would like that. So.
Thank you very much.
Yes. Bye.
Thanks, Anna.
Bye.
Thanks everybody for joining.
Bye.
Have a nice day.